Hi, my name is Lukas Winiwarter, and today I will be presenting to you a virtual laser scanning of dynamic scenes created from real 4D topographic point cloud data. The objective of this research was to use virtual laser scanning, or VLS, to evaluate flight planning for a dynamic scene. Virtual laser scanning is a scientific method that allows you to create 3D point clouds, so you can recreate LiDAR point clouds from models of reality. These models contain a sensor model, which represents the laser scanner itself, a platform model, which represents the device or platform the scanner is mounted on. This could be an airplane or a truck or a static tripod, and a model of the scene. And in this research, we want to investigate how we can transfer a scene from a real data set to such a model, and we want to transfer a dynamic scene. This means that the scene is changing over time. The question that we could pose to justify such a research is we want to figure out what the maximum flying height is for a certain airborne laser scanning study to be able to detect erosion rills. Now, the workflow for doing this dynamic scene transfer is as follows. First, we do a change analysis where we identify changes over time in point clouds. Then we extract a change form that we have identified, quantify the displacement over time. And then we generate a virtual scene acting as a canvas where we can then apply the virtual deformation by just applying the displacement which we have quantified in step 3. In the next step, we apply virtual laser scanning by simulating different acquisitions at different flying heights. Here we use the Helios++ software to do the virtual laser scanning. Then we analyze the results and interpret them to say, okay, at a certain flying height, change has been detected or it has not been detected. The theoretical considerations we have to keep in mind here are concerning point density and point pattern. So generally, with a higher altitude and higher flying speed, we are able to cover a larger area in the same time. This is usually referred to as the productivity of a system. And you can see this in the table here on the rightmost column, where at an altitude of 500 meters above ground, we have a productivity of around 100 square kilometers per hour, whereas with 4,000 meters altitude, we get more than 1,000 square kilometers per hour. Note that also for these higher altitudes, we need to decrease the pulse repetition rate, which will in consequence lower the point density. But we need to do this because we need a stronger laser pulse with more power to be able to scan over larger distances. Also with higher altitudes, we have a reduced point density, as you can see on the bottom right, and a reduced point accuracy due to the beam divergence of the laser scanner. The dataset that we want to use for transferring the scene is a debris-covered slope in Pfalz, Tyrol, Austria, where we see the patterns of rill erosion and some excavator works, which we will not focus on. It is a dense, this means measurement every 2 hours, terrestrial laser scanning time series that was analyzed over the course of 6 days in August 2020. We use a time series smoothing method employing a Kalman filter to be able to propagate uncertainties. This means we start with TLS measurements and alignment errors, so both errors stemming from the measurement itself as well as from the alignment procedure. Then we quantify M3C2 point cloud distances using M3C2 with error propagation and pass these results to a Kalman filter smoother using the RTS smoother. The result then looks something like this. This is now the difference between the first and the last epochs. You can see the change values ranging between minus 10 centimeters and plus 10 centimeters. And this is the erosion rills that we will be looking at. For each one of these core points, we can draw the time series. In this example, this is one of the erosion rills. And you can see why it's important to use the Kalman filter here. If we just use M3C2 with error propagation, we're only able to detect this change is significant very late on here, almost the last measurement. Whereas with the Kalman filter smoother, we can detect it pretty much as soon as it happens. This video shows those changes over time in a 2D bird's eye view. So you can see these anthropogenic excavator works happening here. You see the whole scene sometimes turns a bit orange and sometimes a bit blue. And this is due to the alignment uncertainty. And we can see these erosion rills forming. Sometimes there's also some data gaps in the left most, which is furthest away from the scanner. And these data gaps are due to occlusion from precipitation. If we now simulate on this time series, we can do this simulation from different altitudes and see how well we can detect the erosion rills. And that's what you see here on the left side, the result of an acquisition for a flying height of 500 meters, where you can clearly identify the erosion rills, both in the M3C2 distance plots as erosion and even accumulation on the leftmost of these rills, and also in the binary image of where change is detected as significant, so larger than the uncertainty associated. And on the right-hand side, the same difference, but for an altitude of 3,000 meters. And here you see much more noise in the data. It's difficult to make out the erosion rills, both in the M3C2 distances, but especially in the plot of significant change. And you can now use these plots to make an informed decision of flying height. If you want to be able to detect those rills, and those are the two options you have, you would definitely have to go for the 500 meters ones. We can also simulate this over time and see how we can validate the result. And in this case, we use the TLS measurements as a validation measure, where we use the Kalman filter to test for significant change. And then we can calculate the F1 score with the results obtained from the airborne laser scanning simulation for different altitudes. And you see here that after a certain point in time, here it's the 23rd of August, 3 altitudes kind of all perform the same, an F1 score of around 0.65. So you can pick the highest one of these here, let's say 1,000 meters, because it does not perform significantly worse than the other two. In a spatiotemporal visualization, we can see how at different points in time, change points are detected as significant from different altitudes. So the color here shows at what altitude a change as a core point is first detected as significant change. And by using this information, we can go and say, okay, let's look at this first point in time here on the left and look at this erosion rill. If we want to be able to detect that, we need to find like the most prominent color. Here I would say if we use this sepia brown, which represents 2,000 meters, and include also the salmon colored and the pink colored ones, we will be able to detect this quite well. So from 2,000 meters altitude, we should be able to see what is going on here. For this number 2 rill, at this point in time, we won't be able to detect much, but later on we can even detect it also from altitudes around 1,500 meters, so the stuff represented in green here. To sum up, virtual laser scanning can support the selection of data acquisition parameters and gives you a straightforward way of interpreting the results, because what you see is what you get. If you see the changes in your simulation, you should also be able to see it in the real acquisition. If you're not able to, you won't be able to in the real acquisition either. The 3D scene model that we used here, it should always be derived from higher resolution data to avoid interpolating effects. And higher resolution here means both spatial and temporal. And this allows you then to kind of drag and drop existing change forms that you have a TLS time series of onto new scenes or investigate them with new settings. Overall, this work can provide tools for informed decision making for stakeholders. Thank you very much for your attention, and I'm happy to answer any questions.